Short duration rainfall extremes are a very high intensity of rainfalls that occur in a very short time span, like few minutes up to an hour, and they are intensifying with climate change. As a consequence, the design levels of precipitation we use for sewage systems, dikes and dams and to define insurance premiums, they are being outdated and they can lead to unsafe conditions. Unfortunately, climate models that we have are not able to resolve the convective processes that are at the basis of these extreme events, and the models that can do that are very computationally intensive and cannot provide information on very rare events. Extreme short duration precipitation increases with temperature at scaling rates that are larger than 7% per degree Celsius that is predicted by the well-known Clausius-Clapeyron equation. The scaling rates can change from place to place, and they only hold until some high temperatures are reached. After that, they are found to decrease. This poses problems in using the scaling rates for projecting future extremes. This is where this study comes in. This is a collaboration between the University of Lausanne and the University of Padova. It is within the framework of the Department of Excellence project, and it is also a collaboration with the Department of Statistical Sciences here in Padova. Here we introduce a new statistical model that enables us to use the scaling rates for projecting future extremes. The statistical model is called TENAX and allows us to combine two components. We have a component that defines how precipitation intensities increase with increasing temperature, and one component that defines the probability density of temperatures during precipitation. Combining these two components with the total probability theorem, we are able to reproduce both the scaling rates that are above the Clausius-Clapeyron relation and the decay with high temperatures, thus solving the problems we found before. If we now assume that the magnitude component remains invariant, which is equivalent to assuming that the physics of a process at a given temperature is invariant, we can provide projections of future extremes only changing the temperature component. By splitting historical observations into two periods, indeed, we could predict extreme short duration precipitation for the second period only based on observations from the first period and temperature during wet days for the second period. As wet day temperatures are reproduced by climate models much better than short duration extremes, this represents a significant advancement in our tools to project future extremes. The study, now applied only on Switzerland, can be actually generalized to other locations, and we're now extending it to the entire Alpine range.